Hello everyone. This presentation is entitled Seamless Reconfiguration of Rule-Based IoT Applications. This is a joint work with Francisco Durán, Ajay Krishna, Michel Pallec, and Radu Mateescu. IoT applications are not monolithic applications built once and for all. They are constantly modified during the application lifetime due to removal, replacement, or addition of new objects. Updating an IoT application should be carried out with a specific care because this may induce incorrect behavior or inconsistencies in the application. Such problems must be avoided during the reconfiguration process because they can induce additional costs or hazardous situations. In this work, we propose new techniques for supporting the reconfiguration of IoT applications while providing formal guarantees during the reconfiguration process. These techniques compare two versions of the application before and after reconfiguration to check if several properties of interest from a reconfiguration perspective are preserved. The analysis techniques have been implemented using the mode framework and integrated into the WebThing platform. An IoT application in this work is described by a set of objects and a composition expression consisting of a set of rules. In this work, we rely on an abstract model of objects defined in terms of label transition systems, LTS. An LTS represents the ordering of events actions in an object. A question mark and an exclamation mark are used to indicate that the object is receiving or emitting a value from to its environment, respectively. A simple rule-based composition language is used to specify the composition expression. It assumes if, even, then action rules as basic elements. A rule is triggered when one event is issued by a specific object, and as a reaction, one action is issued to another object defined as target. These rules can be composed to build more complex expressions using basic operators such as sequence, choice, concurrent execution, or repetition of a rule. As an example, the application given below consists of two motion sensors and a bell. This application can be used to notify the entry and exit of customers in a shop. The composition expression consists of two rules. When the motion sensor detects someone entering the shop, it rings the bell, and when the second motion sensor detects someone leaving the shop, it again rings the bell. The composition can execute this rule at any time by using a choice, plus, and an iteration construct, star. The reconfiguration properties take as input the current application with its current global state, and its execution trace, and on the other end, the new application. The seamless reconfiguration property checks whether remaining objects in the new application can reach their current states. This is important because it means that the deployment of the new application is possible without starting again this application from the beginning. A reconfiguration is called a conservative if the seamless property is preserved and if, from the global state in which the reconfiguration is applied, all behaviors that could be executed in the current application are still executable in the new application. A reconfiguration is called impactful if the seamless property is preserved and if the whole behavior of each new object can be entirely executed in the new application. Beyond the reconfiguration properties introduced previously, it is also possible to check classic safety and liveness properties on the new application only using model checking techniques. In this case, this additional verification does not focus on specific global state, but it allows the analysis of all the possible executions of the new application. Going back to the running example, suppose we want to replace application 1 by application 2. In application 2, the entrance is controlled in order to limit the number of people in the shop to 10 people, for instance. To do so, we keep both sensors and add an access control and a drawer. The access control is a software-based counter that counts the presence of customers, detects when the shop is full, and accordingly authorizes or restricts the entry of new customers. Replacing the first application by the second one corresponds to a seamless reconfiguration because the two remaining objects, sensor in, sensor out, have a single state, which is reachable in the new composition expression for any execution trace. This reconfiguration is not conservative, as the bell has been removed and this behavior, ring, cannot be executed anymore. This reconfiguration is impactful because the entire behavior of the new objects, control and door, can be executed according to the new composition expression C'. The reconfiguration properties presented previously can be automatically checked via an encoding into rewriting logic and the use of modes verification tools. More precisely, the mode specification of an IoT application consists of 4 steps, which aim at specifying successively IoT objects, rules, composition expressions, and applications. The seamless property is encoded as a mode operation, which returns a Boolean response indicating whether the current global state for the remaining objects is reachable by executing a given trace. Mozart is built on top of the WebThings platform and supports the design, verification, and deployment of a new IoT application. Mozart provides 3 new components. The first one allows one to design a new application using a user-friendly user interface. The verification component checks that the new and the current application respect the reconfiguration properties, seamless, conservative, and impactful. The third component automates the deployment of the new application. Mozart was applied on several smart home applications for evaluation purposes. To conclude, we have presented some techniques to support the reconfiguration of IoT applications while providing formal guarantees. We have defined several properties, such as seamless, that characterize the consistency and correctness of the application to be reconfigured. All these checks are fully automated using an encoding into rewriting logic and mode simulation and model checking tools. Mozart implements the ideas presented in this paper and was applied to several smart home applications. Thank you very much for your attention.